For our sensor, we need very fine structures, maybe in the 10 micrometer range. And that means we need substrates which are of very high quality. They must be very smooth. On the other hand, again, for the circuit, we would like to have something relatively cheap. And again, that would be a printed wiring board. And for that reason, we can also combine such thin film sensors, which are on a flexible foil, with a printed wiring board. Also, it is important when we want to measure a force. This force is typically measured on a reference body, like a steel strip or so. And so it's very important that the influence of the sensor on the stress is low, and so we want to have a thin film circuit. And for that reason, we combine a flexible circuit, like here or here, with a printed wiring board. In printed wiring boards, we are not confined to soldering just a device on top of that board. In the last years, there have been other ideas. For instance, you can take two half printed wiring boards, and in between these, you bring the chip. That chip is interconnected, for instance, with technologies which we use to make multi-layer boards. And in that way, we have printed wiring boards where the devices are not on top, but they are inside the board. Here we can see an example that's just a cut of such a device, or as we can see here, it's an X-ray image. The devices can only be seen in X-ray. From the outside, this printed wiring board just looks like a flat plate. And that helps us to make much flatter circuits. And in that way, you could also make big printed wiring boards, which are as thin as a chip card, for instance. Other ideas, maybe they are more in the idea state, is how can we make intelligent clothes? Yeah. So, for instance, for sports, you could like to have some sensors in your shirt, and such sensors could measure your temperature, your humidity, your heartbeat, and so on. Of course, it's always possible to make a small box in a pocket and there to concentrate all of the electronics. But here the idea was, can we make smart clothes where the circuit is really made on the stuff from which your clothes are. And here was some idea how to bring silver wires into such a blue jeans cloth, and in that way to mount some display or to mount some sensor, or here it is something which is touch sensitive. I think doing it that way is a little nonsense, but on the other hand, it shows us what ideas for modern assembly and packaging are. Here is something more serious. Many people in Germany need an artificial sphincter. So it's a total of 20,000 patients in Germany, as Professor Voyas told me, and it can be up to 8,000 new patients per year. And for instance, that can happen when your sphincter, your natural sphincter, is paralyzed, for instance, due to a virus infection or due to cancer. And in that way, people are in a very, very strange situation. And for that purpose, Professor Voyas, he designed a prosthesis for the sphincter. That sphincter can be built up, can be implanted into the backside of the patient, and here you have something which can be blown up, and so if it's blown up, it is contracted, the sphincter is contracted, and so you have a tight closing here, and by some remote control this can be opened, and then you can have stool. Okay, that's something which is important, and again, that's a special case of assembly and packaging. I must say, my assembly and packaging is mostly for industrial applications. I do hardly any work for assembly and packaging for implants, for instance. That's mainly the business and the competence of Professor Stieglitz and Professor Woyers here. So if you are interested in such cases, please address my colleagues. Okay, now what do we need in assembly and packaging to make systems? Let's say we would like to have a integrated, we would like to have a sensor. So we need a sensor. Typically, it's already a CMOS integrated sensor. We need different other components which have to be assembled, for instance, by soldering, as we can see here. For the passive devices here, we have some, I don't know, it's a diode and some capacitor, for instance. We have integrated circuits. These can be passive or these can be IC devices. What we always need is a substrate. In our case here, it's a semi-flexible substrate, so it is bent in some way. And after all of this has been assembled, of course we need an encapsulation which we cannot see on that image. Again, coming back to build such systems, we have 3 legs on which we stand here. One leg is the fabrication processes and the technologies. That's how do we build it. The second is from what do we build it. It's the materials and properties. And the third is the concept. So the complete system must be designed in a sensible way, so it must be possible to produce it economically. It must be reliable. The APT must not deteriorate the properties of the chips, and so on. So we have 3 aspects of that lecture, and all of these aspects are important altogether. Okay, here a colleague in Erlangen, he has a very big institute with more than 100 persons of staff, and he has one of the biggest institute in electronics manufacturing, and they put together what is necessary in technologies for assembly and packaging, and we can see here it's extremely complex. And for each let's say, a branch of assembly and packaging, there are different solutions here, yes, for the substrates, for the patterning, metallization, for the interconnection, for the protection. And so what I would like to try here is to bring some order into that system. So it's a lecture dealing with something which is very complex, but on the other hand, it is important to understand it, because as embedded systems engineers and microsystems engineers, you must be able to design and understand such systems. Okay, here is also something which is a little more funny. That's not a really serious application. Here we have a plastic housing. Again, on that housing we have some structures, And that shows us a trend we have now in technologies. That trend goes to additive manufacturing, and additive manufacturing also means digital manufacturing. So for instance, we have a 3D printer, and that printer can be used just to print here a capacitive structure, though that would be a sensor for humidity sensing. Again, that example is not really serious. My colleagues, they just did it to show what is possible. But that's a trend, using printing technologies, using technologies which do not need masks or tools, but just technologies where you generate the structures from something which is liquid or semi-liquid. Also for devices, you can do such embedding. Again, here we have some written interconnection structures, and also this body of the package is done, and that process is so-called stereolithography. And in that way, one can also create 3D structures. Why is it also important to deal with assembly and packaging? When you look at more complex electronic systems, here that's, for instance, electronics for a cochlear implant, you could say the IC which we use is so small. Yes, that's the IC. And the rest of the system is plastics, metals, housing, substrates. So typically here we could say, yes, more than 95% of the mass or of the volume size are assembly and packaging. So most of the materials which are used are for assembly and packaging, not for the silicon. On the other hand, having such large portions costs lots of money, and always the costs of assembly and packaging are much higher than the costs of just creating the IC. Okay, that makes it important, and if you want to earn money, you must make your assembly and packaging cheap and as economic as possible. The electrical behavior is also affected significantly by assembly and packaging, and something which I forgot here, which is not so important here, but it's the thermal behavior. Both are very important and mainly affected by assembly and packaging. Also, many studies which we performed that were showing that from the failures, 50% were related to assembly and packaging, and the rest of the failures were related to the IC. So that means assembly and packages also make systems more unreliable, and that's again an important argument to make assembly and packaging as good and as powerful as possible. Okay, here we see such examples. For instance, we can see cracks in solder joints, cracks in the solder joint on a pin of an anti-brake locking system. We can also build in defects if a device is already defective from manufacturing. Of course, its lifetime will be significantly lower than the lifetime of a good sample. We can have cracks we generate in the chip due to bonding processes, and in that way assembly and packaging is not only important for the reliability of assembly and packaging, but also for the reliability of the IC or of the chip. In fact, On ICs, we have roughly 20 different failure modes. On printed wiring boards, we have possibly another 10 failure modes, and there are 10 physical failure causes. A failure cause is something like a temperature, humidity, impurity, and so on. Okay,